we started with informal description of routing last week. We'll continue on routing shortly and for most of today. Just everyone submitted the assignment. I think all groups have a website. I haven't checked the individual details of the website, but I've at least checked that all groups have something on a website. Over the next week or two, I'll check and give some feedback on the assignment. What are some of the things that you may have learnt in the assignment? Okay, you may now understand a bit more about how wireless LANs work. You may understand how to use Wireshark. Wireshark's a common piece of software for diagnosing problems in networks. By looking at the details of what's sent across a network, you can try and work out if there's something wrong or you understand what's happening. So that's what you learn about Wireshark. What else? How to set up a basic wireless LAN. You may have learned how to set up an ad hoc network in some cases. Some of you done your experiment using a direct computer-to-computer link between two wireless laptops. How to create a website. Well, that was not so hard. So they're some of the main things that most groups would have picked up from that assignment, and really applying some of the knowledge that you've learned in the class in a practical setting. This is a slide from the next topic on LANs, but it puts into perspective wireless LAN with respect to our 5-layer stack. So here's our 5-layer internet stack from physical layer up to application layer. You studied wireless LANs, how I connect my laptop to the access point. And you realise that that uses a standard or a set of standards created by IEEE. IEEE is the organisation that creates standards, electrical standards, including networking standards. And specifically, they have a set of standards under the number 802, okay, which covers technologies for local area networks, and they also cover metropolitan area networks, which is, say, to cover a city and so on. In fact, it also delves into wide area networks now. So they've created many standards in this architecture over many years. For example, well, the one that you saw is 802.11, and there's a set of standards that fall under that number. It's just a number to refer to some documents for a particular standard. There are many variations. So you may have seen 802.11a, 802.11b, and so on, which are just amendments or changes to the standard. So there are standards for wireless LAN or Wi-Fi. And there are also standards in this 802 architecture for other technologies. The main other one is wired LAN, that you plug your cable into your laptop or PC at home for wired LAN access, generally referred to as Ethernet. And it's been improved over time, and the improvements have been referred to as fast Ethernet and gigabit Ethernet, and there are others. And that is the 802.3 standard, defines how Ethernet or wired LANs work. 802.11 Wi-Fi, and there are others. An older LAN technology, token ring, 802.5, and others. Bluetooth fits in here, other wireless technologies, and it goes up to, I think, I don't know whether it's 21, 22, even more. They keep being developed. They focus on the physical layer and the data link layer. You can see here that how it most commonly works is that for each technology, wireless, token ring, Ethernet, there's a standard for, or one or more standards for the physical layer. You may have come across things like 802.11a, b, g, and n. And you may have seen that or you should have seen and noted in your assignment that they give different characteristics, especially data rates. So 11b had a maximum data rate of 11 megabits per second, G went up to 54 megabits per second, N even more. They are physical layer standards. They've been improved over time. So as the technologies get better, they come up with variations. And there's also a medium access control standard, which is normally common. Do not worry about, this is one of those later slides. We're going to go back to routing in a moment. Just something related to the assignment. Medium access control. And I haven't read anyone's assignment yet, but what I'll be looking for, if you get full marks, is a description of how the medium access control works. And that is when you have multiple laptops all wanting to talk to that one access point, which one talks first? Which one transmits their packets or frames first? Because they all want to transmit to the access point. If they all transmit at the same time, they'll interfere with each other. And the medium access control, the main purpose is to make sure if many want to transmit at the same time, come up with some rules so that only one transmits at a time. You take in turns, for example. I'll be looking for some descriptions of how that works. We'll see who gets that. Similar with the other technologies, there are physical layer and MAC layer protocols. And there's a common logical link control protocol, 802.2, which is used in most, if not all of these. So physical layer and the 802 LANs and even wide area network technologies in the IEEE 802 series fall within the physical layer and data link layer. So you spend a lot of your assignment understanding some practical aspects of Wi-Fi, wireless LAN. We may return to that when we come to local area networks, but in fact we're going to go through local area networks quite quickly because you study it in the assignment. Today we're going to look at routing. A reminder from last week, the goal is to find the best path from source to destination through a network. We have a source A, we want to reach F, there are multiple paths, find the best path. Well, what is best? Well, we need different performance metrics to measure, or we can select from different performance metrics to measure what is best. It's up to the user or the network operator to select what they consider to be the best. Is it the shortest number of hops, or is it financial cost, or something else? In our examples that we'll go through, we're going to use small networks so we can draw them and see how they operate. In real life, networks may not be so small. There may be networks with hundreds of nodes. And when the networks are not small, then you need some automated approaches for determining the best path. You need some computer software to calculate the best path. And importantly, if I find the best path from one node to another, and then over time the network changes. Nodes appear and disappear, link costs may change. So today the best path may be from node 1 to node 6. Tomorrow it may, node 1, 4, 5, 6. Tomorrow it may be a different path. In networks, because of the network characteristics change, the best path may change over time. So we need automated techniques for calculating the best path and finding information about the best path, so we get routing protocols, which we'll cover today. A routing algorithm needs to find the best path. In general, it has a number of requirements. Say the input to the algorithm is some information about the network. The output should be a set of paths, the best paths, or a path from one source to one destination. The requirement of such an algorithm, of course, it should be correct. That is, if I ask of this network what is the best path or the least cost path from node 1 to node 6, and here we have cost metrics on each of the links, but you have this on one of your later slides. The algorithm should return the least cost path is 1, 4, 5, 6, because the cost is on this link 1, this link 1, and the next link 2. The path cost is 4 in this case. And if you checked all the other paths from 1 to 6, 4 is the least cost path. Okay, that's the best one. If my algorithm returns something else that is not the least cost path, it's incorrect. Okay, that's an obvious requirement. We need to choose the correct paths. Our algorithm should be simple, so it's easy and cheap to implement. If we need to have computers running this algorithm, we want to minimize the amount of overhead in running the algorithm and performing the calculations. It's simple to use some computer software to calculate all the least cost paths for this network with 6 nodes. That is, it would take milliseconds to calculate. But you expand that to thousands of nodes, even hundreds of nodes, and algorithms like Dijkstra, Bellman-Ford algorithm for finding least cost paths may take a non-trivial amount of time, possibly seconds, even longer. And if we need to continuously recalculate, we may spend a lot of time calculating to find what is the best path. So we'd like to have simple approaches so we don't waste too much time on calculating, and also and finding information about the network, we do not produce too much overhead. So an algorithm is correct, simple. An algorithm that finds paths, and the algorithm should be robust. What that means is that it should be able to cope with changes or errors in the network. For example, in this network, if we calculate the path from node 1 to node 6 to be 1, 4, 5, 6, but the network changes. And over time, this link, the load on this link, the amount of traffic on this link goes high, increases, and eventually it's overloaded. That is, there's a lot of traffic on there and everything's slowing down by sending through this link. Then an algorithm ideally should be able to identify that and possibly choose an alternate path that avoids that overload. So if we have a problem, say on this link, then we'd like a routing algorithm to be able to avoid such a problem. That's what we mean by robustness. In the presence of errors or overload, find an alternate path. A conflicting requirement is that the path changes should be not too frequent. Stability in the paths. I choose the path 1, 4, 5, 6. I notice something changes, so now I choose an alternate path 1, 4, 3, 6. But then something changes here, so I choose another path 1, 4, 3, 5, 6. And the network characteristics are changing over time. That is, the amount of load or the amount of packets being sent across links through these nodes changes over time. If I change my paths too frequently, that can cause problems with some applications. So stability is about, if I choose a path, let's make sure that that path, we can use it for a long period of time. Let's not change it every millisecond. If by changing paths, one problem that occurs is that your packets start going along different paths. The first packet I send goes from 1, 4, 5, 6. The next packet goes 1, 4, 3, 6, and so on. If packets start taking different paths, then they may arrive out of order at the destination. The packets may need to be reordered at the destination, and reordering of packets causes problems for some applications, video for example. So generally we'd like an algorithm that will choose paths which are stable, that do not change very often. That's stability. But on the other hand, we'd like an algorithm that if we detect some problems, that it can change paths. So don't change too often, but change often enough to avoid errors in the network or overload in some parts of the network. So there's a trade-off there amongst those two. This one's obvious. Choose the best path. Choose the optimal paths. It's obvious as a requirement, but sometimes not easy to achieve. We use some examples about driving. Okay, today you know the best path to drive into Bangkok, and you take that path. So you start driving along that path, you checked on the websites, you checked on the radio, you spoke to your friends, and you found out where all the traffic is, so you calculate the best path to drive into Bangkok. You get in your car, you start driving, you're on the way, and there's an accident at some intersection, and now that path that you chose is no longer the best path. It's a suboptimal path. There may be a better path. So we'd like to choose the best path, the optimal paths, but in practice, again, things change over time. In the network, we choose the best path from 1 to 6 as 1, 4, 5, 6. We start sending packets, but if the cost of this link goes up, then it may no longer be the best path. So try and choose the best path. Efficiency, I'll come back to fairness in a moment. Efficiency, when we want to choose a path, we need to know something about the network. If node 1 needs to choose the path to node 6, it needs to know the costs of all the links, which nodes are in the network, and who they have links to. So this computer needs to know about all of this information to calculate the least cost path. How does it know that? These 6 nodes are computers or devices across Thailand, for example, a network connecting different cities. How does this computer know about, so in Bangkok, know about some other computer, some other switch in Chiang Mai? How does it know about the links that this node has? Because it's not directly connected to node 6. How does it know about the cables or the links going into node 6, and especially the costs of the links at node 6? So the question is, how does one node learn about the topology and the costs of links for the rest of the network? Well, they need to exchange some information. For example, node 1 needs to send a special packet to the other nodes, telling the other nodes about its links. And hence, and all the other nodes do that, and you can learn about the nodes, the links, the link costs in the network. We need to exchange information between the nodes to learn about the network topology. That introduces some overhead. The more information we exchange, the more overhead of sending this information. We'd like to be efficient and minimize this overhead. The more information we exchange, generally the more optimal our paths will be. And the more often we exchange information, but the more often we exchange information and the more we exchange, the less efficient we'll be. That is, we'll create more overhead of exchanging this information. It's like, okay, again, drive into Bangkok. What I do is I check a website to find about traffic conditions. If I check it once a day in the morning and then, find out about the traffic conditions for at this point in time, then I choose my path in the afternoon to drive. Then the problem with that is that I check in the morning and then drive in the afternoon. Between the morning and the afternoon when I start the drive, there may have been some changes in the traffic condition. I may not get the optimal path. So what do? I check this website every 5 minutes. By 5 minutes I check the website, I keep checking the website and keep updating my information about the network. More chance of getting the optimal path, but I spend more time checking the website. So in terms of our network, we need to exchange information, learn about the network. But the more often we do that, and the more information we exchange, the larger the overhead, the lower the efficiency. So there are some trade-offs here. Fairness is a difficult one to describe. Fairness is about trying to choose paths which are fair to all stations, to all nodes in the network. A simple but maybe a little bit unrealistic example is we have some network. These are switching nodes. Let's say we want to choose a path from node 1 to node 6. And so node 1 wants to find a path to node 6. And similar, node 2 wants to find a path to node 6. And we apply some algorithm to calculate it automatically for us. If it calculates for node 1 to node 6 the path 1, 2, 3, 4, 5, 6, whereas for node 2 to 6, 2, 7, 6, in some cases we can consider this unfair in that for node 1 it gets the longest path, but node 2 gets this shorter in terms of number of hops path. Depending upon the metrics we use, we can potentially have algorithms that do this, and that they choose the worst path for node 1 or a worse path than node 2 gets for getting to that destination. So node 2 gets a good path, node 1 gets a bad path in terms of it's long. We would say that's unfair for node 1. We'd like an algorithm such that it doesn't matter who the source and destination is, they are treated equally. That may arise in very special circumstances when it depends upon the metrics and the algorithm used. But it's possible that an algorithm may choose paths which are good for some nodes but bad for other nodes. We'd like it to be the same for all nodes. I think we'll not try and give another example of that. It's hard to see or hard to illustrate on a diagram. But there are the requirements that we be fair amongst all stations so they get equal performance. Again, that may have some trade-off with optimality and even efficiency. So to get the optimal paths, it may not be fair in some cases. Some nodes may be treated worse than others. So these are some of the general requirements we need for a routing algorithm. Let's go and look at some of the cost metrics and some of the ways in which we update information. Last week we mentioned the terminology. We're going to use this example network where we have 6 nodes, a number of links between those nodes. We've assigned costs to each link. The costs have no units here. They could be anything that we want. It could represent a financial cost of using that link, or a delay of using that link. It takes 1 millisecond to send a packet from 1 to 4, as an example, and 7 to send it back. But we've assigned some cost to links, and we'll use least cost routing. To choose a path from one node to another, choose the path with the least cost, where the cost of a path is the sum of the cost of the links on that path. We also refer to hops sometimes. That is, the number of hops from node 1 to 6 via 4 and 5 is 3 hops. Okay, this is some terminology from last week. So, some of the things that we need to understand with routing is how do we select a path? When do we select a path? So which metrics can we use is the first one. When to select a path? Do you select a path every time you want to send a packet? Or do you select a path at the start of each day and tomorrow you calculate a new path? Or do you just select a path once and never update that? Who selects the path? What information or which nodes provide information about the network status? Again, for node 1 to select the path to node 6, it needs to know that there are these other nodes in the network. It needs to know that node 5 has links to 4, 3 and 6. And to select the best path, node 1 needs to know that node 5 has these 3 or these links and the costs of those links. So the information about the network topology, the nodes, the links between the nodes, the link costs, so links have some cost assigned to them, and the current usage. Over time, the usage of a link may change. That information needs to be known to all of the nodes in the network to calculate the best path. Who provides that information? Where do we get it? And how often do we update it? Some answers to those questions are listed here. We'll talk about some of them and use some examples. For example, the first question, which was what performance criteria, or I call it what cost metrics can we use to find the best path? That is, where do these numbers come from? What does it represent? Some common metrics, some common ways to measure the cost of a link include the number of hops. That's sometimes the first thing that we think of. When I ask you, maybe on the board here, what's the least cost path from 1 to 6, I think most people would think 1, 2, 7, 6, because the number of hops, 1, 2, 3, is the least. So that's the obvious one, is the number of hops. But sometimes using a hop may incur a larger cost. For example, if sending packets across each link has some delay, the delay of this link is 2 milliseconds, 2 milliseconds, 2, 2, and 2. The delay of this link is 100 milliseconds and 1 millisecond. Now, if I care about getting my packets from node 1 to node 6 quickly, with least delay, the best path would be 1, 2, 3, 4, 5, 6. So delay is another performance metric, another cost metric that's commonly used. If you know the delay of your links, you give them a number, a cost, and then the algorithm chooses the best path based upon the least delay. Financial costs, so cost here means financial cost. If we think of networks across the globe, across the world, connecting between different countries, someone needs to pay for the traffic to be transferred between different nodes. So choose a path which minimises the financial cost. Throughput. Sometimes we want to choose the fastest, not in terms of the least delay, but if we've got a lot of data to send, it doesn't matter if it's a 103 millisecond delay or a 10 millisecond delay. If this path gives me an aggregate throughput of 1 megabit per second and this one 100 megabits per second, then I would like to use the 100 megabit per second path. So sometimes throughput is a metric. So there are different ways that we can measure what is the best. Okay? It's usually up to the operator of the network to select those metrics. SIT has some nodes inside and between the two campuses, and they need to perform routing, so they need to select the metric that they want to choose the best path. The simplest is usually the number of hops, but you can make it more advanced. It doesn't have to be performance metrics, it could be political metrics. For example, choose a path such that your traffic will not go through a country that you do not trust. Okay, so you need to send your packets from Thailand to the UK. There are different paths through the world. So if you have security requirements and you don't trust sending packets through a particular country, then choose a path that avoids that country. So routing can, in theory, do that as well. So some examples of the performance criteria. That is, how do we get these numbers? Once we choose a performance criteria or a cost metric, then we use that data to create these costs, these general costs assigned to links. Once we assign these costs to links, these general costs, we can use some algorithm to calculate the least cost path. It's just the path with where the sum of those costs is the least. When do we calculate the least cost path? If we remember back to switching, if we look at packet switching, with datagram packet switching, we send one packet and then the next packet, and they are treated independently. They potentially may take different paths. So one approach with datagram packet switching is, okay, I have 100 packets to send from node 1 to node 6. I have many packets to send from node 1 to node 6. First packet, choose a path. In particular, choose the next node to send to. The next packet, I may choose again, and it may be a different path. So that's one extreme case where for every packet, we decide which path to take on the individual packet basis. If we were using virtual circuit packet switching, what we do is we set up a connection from node 1 to node 6 and then send all our packets along that connection. So when we set up the connection, we choose a path then. And then we do not recalculate the path, we just send all our packets along that one path. So there's different approaches for when do you calculate or when do you make the decision of which path to use, on per packet or per connection or session. Which node makes the decision of which path to use is another question. We can have a distributed or centralized approach. A centralized approach would be, let's say we have some other special node, node 0. And all of these 6 nodes have some special link into node 0. Node 0 calculates the best path for the entire network, and whenever a node has to choose a path, it consults node 0 and it tells it which path to use. That would be a centralized approach. There's one central computer that does all the decision making for all the nodes. A distributed approach is there's no central node here. The individual nodes make decisions by themselves. Okay. We'll see that that's the common approach. We'll see when we look at routing tables shortly some different ways to store that information. What that means is node 1, or an example of distributed is node 1 wants to send packets to node 6. Node 1 chooses one of the 3 neighbours it's going to send to. Node 1 has links to 3 nodes, node 3, node 2 and node 4. Node 1 chooses to send the packets to node 4. Node 4 receives the packet. The destination is node 6. So now node 4 makes a decision. To reach node 6, node 4 has packets coming from node 1. To reach node 6, it makes a decision. Do I send to 2, 3, 5, or back to 1? Well, don't send back to 1. They just sent it to us. So it chooses from its 3 neighbours, and let's say it chooses node 5, sends the packets to node 5. Node 5 has the packets destined to node 6 and now makes a decision. Do I send them via 3 or send direct to 6? Okay, for example, sends to 6. So in that case, a distributed approach, each node makes a decision of where to send the packets as they receive them. The last case is the source node chooses the path. Node 1 wants to reach node 6. Node 1 chooses the path, 1, 4, 5, 6. And possibly inside each packet, it includes some information about the path to take. So what node 1 does, creates the packet, puts in the header, for example, the set of nodes it wants to send it via. 1, 4, 5, 6. Sends that packet to node 4. Node 4 receives the packet and sees, okay, the header says node 4 needs to send to node 5. So node 4 simply sends to node 5 based upon what node 1 told it. And similar, node 5 looks at the header of the packet and realizes, okay, I need to send to 6. So slightly different between the distributed and source routing. In the source routing, the source node calculates the path and informs the nodes along the path where they need to send it. So the source node chooses the path. In distributed, each node independently chooses the next node to send it to. Hopefully, both approaches will still choose the best path if things are set up correctly. And centralized is there's some special node that does the decision making for all the nodes. So, for example, node 1 wants to send to node 6, it asks the central node tells it, send to node 4. Sends the packets to node 4. Node 4 has packets destined to node 6, asks the central node, says send to node 5, and therefore sends to node 5. So that's a centralized approach. So when do we decide which path to take? And who decides which path to take? Different approaches. Then the last two are about how do we get updates of the network topology and the link costs. How often we get them, and where do we get the updates from? Node 1, imagine these 6 nodes are distributed across Thailand. They have links between them. What does node 1 know about the network when it turns on? So node 1 is a switch, a computing device. Someone turns it on. What does it know about the network? What does node 1 know about the network? It most likely would know its adjacent nodes or its neighbours. Node 1, okay, it knows about itself. Okay, it knows, so it's a computing device. It knows how much memory it has, the queue sizes, and so on in there. When it turns on, the queues will be empty. As it starts creating packets or packets to send, the queues may build up. So it knows about characteristics of itself. Okay. And it has a cable, or it has multiple cables coming into node 1. If we draw node 1, some computing device, then there are at least 3 cables coming into it. They may be full duplex cables. That is, one of them going to node 3, one of them to node 2, and one to node 4. Of course, node 1 should know about that it has 3 cables plugged into it, and probably knows some information about those links. So we would say that the information that node 1 knows about itself and about those links are information that is local to that node. Okay? The information about the network that node 1 knows is local to that node. So that would include node 1 has links to 3, 2 and 4. So let's record what node 1 knows. It knows there's a link from 1 to 2, and it should know about the cost of that link. Let's say the cost is some financial cost, or if it's a delay, then it's quite easy, or it should know what that cost is. It can measure the cost if it's delay, for example. So a node, we assume, normally knows information about itself and its directly attached links. It knows there's a link from node 1 to node 2, and the cost of that link is, in this example, 2 units. And there's a link from node 2 to node 1, and the cost of that is 3 units. And other links, that is, these are the 4 links. So we'd say that information that node 1 knows about these 6 links as local information to node 1. It doesn't know anything about node 5, node 3 or node 6. Sorry, node 3 it does, 5 and 6 it has a link to 3. So considering just local information to node 1, it doesn't know that node 5 or node 6 exist in the network. Its picture of the network is simply there are 3 other nodes and there are these set of links here. Let's try and record them. In red, this is the information known by... You shouldn't try to draw this because it will become too complex. The red part is what is known by node 1 if we consider just the local information. It knows nothing about these links and nothing about node 6 and node 5. Now, if we use just that information and we want to choose a path to node 3, okay, I want to send packets from node 1 to node 3 using just that local information. Will I choose the optimal path? Node 1 wants to choose a path to node 3 using just local information. Does it choose the optimal path? No. What path does it choose? If node 1 wants to send to node 3, it only knows local information. Which path does node 1 choose? You said 1, 4, 3. But node 1 knows nothing about the link from node 4 to 3. That's not local to node 1. Considering just local information, node 1 knows that 2, 3 and 4 exist. It knows the cost of these links and these links. It doesn't know that this exists, so I could remove that from the perspective of node 1. So now if you want to choose a path from node 1 to node 3, in fact there's just one path, direct, with a cost of 5. So if it sends its packets across that path, it incurs a cost of 5. But we know that there's a better path, 1, 4, 3. So if we use just local information, we would get a suboptimal path here. We wouldn't get the best path. What we can do is to get more information about the network, ask our neighbours about their links, our adjacent nodes. So node 1 knows about its local links and it knows there are 3 other nodes, 2, 3 and 4. So now let's send a special message to node 4 saying, please tell me about your local links. And node 4 would send back a message giving it information about its neighbours. So what does node 4 know? Node 4, the local information to node 4 is node 4, 1, 2, 3 and 5 and the links between them. That's the knowledge of node 4, this part here. So node 1 sends a message to node 4 and node 4 sends back information about these links. As a result, node 1 has now learned that there's another node in the network, node 5, and there are some other links in the network. In particular, these set from node 4 to node 2, node 4 to node 3, and node 4 to node 5. So by asking your adjacent nodes, or your neighbour nodes, about their links, this node can learn more about the structure of the network. And similarly, it may ask node 2, and therefore learn about this link. And ask node 3 about its neighbours, and would learn about these links. And now has learnt that there's a new node, node 6 in the network. Now, node 1 wants to send a packet to node 3 using the updated information. It calculates the least cost path. Which path does it choose? node 1, node 4, node 3 in this case. And in fact, that is the optimal path. 1, 4, 3 has a cost of 4 in this case. Sorry, wrong. There's a better one. 1, 4, 5, 3 it would choose. It knows that information we see in red here because node 3 and node 4 both sent information to node 1 about their links, and from that we can find that there's a path 1, 4, 5, 3 with a cost of 3. So now it can choose the optimal path. By learning more information about the network, more chance of getting the best path. So that's getting information from adjacent nodes. But note, to do that, node 1 had to send some packets to its neighbours. Node 1 had to send something to 4, 2 and 3, and they had to send something back. That's some overhead in performing routing. That's something to learn about the network. The more information we learn and the more often we send those packets, the larger the overhead of learning that information. The extreme case is to ask all the nodes in the network about their networks. Using just the adjacent nodes, node 1 knows everything except it doesn't know there's a link between 5 and 6. So if node 1 chose a path from node 1 to node 6, it could not use this information. And in fact, it would again get the suboptimal path. It will have to go via node 3. So you can expand. So ask your neighbours, or ask your neighbours' neighbours, ask your neighbours' neighbours' neighbours, or eventually just ask everyone in the network, please tell me about your links. And the more other nodes we ask, the more accurate picture we have of the network, and therefore the more chance of selecting the optimal path. But the more nodes we ask, the larger the overhead in collecting that information. So in the extreme case, ask all other nodes in the network. That's okay if there's 6 nodes, but if there are 100 nodes or 1,000 nodes, sending messages to 1,000 other nodes, and every one of those 1,000 nodes send messages to everyone else, that overhead can go up to be very high. It can be a problem. There are some other alternatives there we will not go through. So this is about where do we get the information about the network from. We can use our local information, that's easy. We always have that. We can ask our neighbours, that's not so hard, but we introduce some more overhead. We can ask all nodes, which gives us the best information about the network, but introduces the most overhead because we need to send more packets. We could collect no information. Let's say node 1 knows nothing about the links in the network. It doesn't know the costs. It doesn't know who the neighbours are. Can we perform routing? Node 1 doesn't know it's linked to 2, 3 and 4. It has cables plugged into it, but it doesn't know the costs of those cables, knows nothing about the other nodes. Can we get a packet from node 1 to node 6? How? Yeah, send to everyone. So even if we know no information, that is, node 1 doesn't know anything about these costs, it still has 3 cables plugged into it. To get packets to everyone else, or to some other node, node 6, just send a copy to across all of these links. 3, 2 and 4 will receive a copy of the packet, and then they do the same. 3 receives a packet. It doesn't care where it's sending, it just sends a copy of that one packet on all of its links. 2, 4, 5 and 6 will receive it. We've reached the destination. Okay. If we want to get a packet from node 1 to node 6, just send to all your neighbours. And then all your neighbours will send to all their neighbours that same packet. And eventually the destination will receive. So we can route information, or we can get information to the destination even if we don't use any information about the network. We'll see we've got flooding as an example of that. So we'll see a more detailed example of how to do that later. This is where we get the information from. The last part is how often do we update that information? We can continuously get update of the information. That applies for local information. We think this node, node 1, always knows about the usage of its links because it is using those links. So it has continuous information about the usage of its 3 links. We could do periodic updates. Node 1 periodically sends a message to 2, 3 and 4 asking them, tell me about your links. Has anything changed? Because remember, the costs may change. 3 may go up to 4 over time. So every 1 minute, send a message to your neighbours saying, tell me about your links. So periodic updates. If something major changes in the network, you could do an update, particularly a topology change. If this link fails or someone unplugs the cable, there's no link to node 2, this disappears, then that could be a trigger to tell other nodes about the change. So we could trigger to tell it to perform updates based upon some major change in the network. Say a link is turned down, a node disappears or is turned off. So there are different triggers of when to perform an update of the information. The more information you collect and the more frequent you collect that information, the more accurate picture of the network the node has, and therefore the more chance of choosing optimal paths. That's good. More information, more updates, optimal paths are chosen. But the more information collected and the more frequent you update, the larger the overhead in collecting that information. So there's the trade-off. You need to consider selecting optimal paths versus producing overhead into the network. They are the design criteria for different routing approaches. So in practice, a routing approach may choose one or multiple of those different options. A simple routing protocol will see flooding uses no information. Therefore, there's no overhead of collecting it, but it has other problems. Practical routing protocols usually collect information about at least adjacent nodes, and in some cases all nodes, and have periodic updates of that information. Let's look at some strategies, some ways to perform routing. The first approach is simple. Choose a route, use it forever. I build a network across Thailand, has 20 nodes in different cities with links between them. I built the network, I know where the nodes are, I know the costs between the nodes, so I know all the information about the network topology. I calculate, so before I turn on the network, I calculate the least cost paths, program those paths into each node, turn on the network, that is turn on every node, and for the lifetime of that network, they use those programmed routes or paths. So this is an example of fixed routing. When we build the network, we calculate the least cost paths from node 1 to all other nodes, store that information in node 1, similar for node 4, calculate the least cost path, store it in node 4, and start sending our packets in the network. Tomorrow we'll use the same paths, next year we'll use the same paths. Okay? It's a simple approach in that we perform the routing just once. The routes are fixed. All right, in practice there may be some exceptions. If we make some major change to the network, we may update it. That is, the network's running for 6 months, then I decide to add another node into the network, okay, in a different city. And therefore, I may recalculate the least cost paths. So on an irregular basis, we may update that. Maybe there's a major change. The good thing about this approach is that there's little or no overhead of collecting information about the nodes. I just do it once. Find out all the nodes, calculate the least cost paths. There's no asking your neighbours about the updates of the cost of links. There's no overhead involved here. The bad thing about this approach is if a link cost changes over time, if the cost is related to the amount of traffic or the amount of packets going through it, then we may choose suboptimal paths. Okay? That is, I choose the path based on this network, but in 1 month's time, or even tomorrow, this link, the cost has gone up to 100. So the path from 1, 4, 5, 6 is no longer optimal. With fixed routing, it doesn't care. It will still keep using this path because we only calculate it once. We fix the routes for the network operation. It's simple. You assign the routes at the start and then do nothing. It's not very flexible. When the network is running, it doesn't cope with changes in the network conditions. So as people send more packets, then it's possible that the costs change. We should deal with that. Fixed routing does not. How do we calculate the least cost path? There are algorithms that will do that for us. You know Dijkstra's algorithm. Maybe you studied also Bellman-Ford. So in the exam, you will answer a question about Dijkstra algorithm in the exam. Yes? Okay, good. I'll create one for you. I think you've studied the algorithms for least cost routing. We're not going to study and recap on how those algorithms work. We assume that there are some algorithms that, given this information, will find us the least cost paths. Okay? We calculate the paths and store information about the paths in the switches, in the nodes. And when a packet is sent, it looks at that information to determine the next node to send it to. In our example network, how many paths do we need to calculate? How many paths? For the entire network, how many paths do we need to calculate? And what are they? The simplest one is the first question, how many there are. What are they? Takes more time. Anyone with an answer? How many paths in this network? I want to be able to get a packet from any node to any other node. Oh well, if you cannot tell me the answer, let's calculate the answer. Let's list them all, or at least start listing them. Source node, node 1, wants a path to node 2. What is it? What's the least cost path from node 1 to node 2? Node 1, direct to node 2. Cost, I'll just put in brackets there, is 2. All right. Another path, node 1 to node 3. Least cost path. 1, 4, 5, 3 is the least cost path from 1 to 3. This path is 2 plus 3 is 5. This is 5. This is 1 plus 3 is 4. 1, 4, 5, 3 is the best one. with a cost of 3. Node 4, 1 to 4, easy. Node 5, 1, 4, 5. Cost of 2. Node 6, 1, 4, 5, 6. We've covered that one. With a cost of, what is it, 4. So for node 1 to reach any other node, there are 5 paths. We need to calculate them, and then we need to do the same for the other nodes in the network. From node 2 to the other 5 nodes, node 3 to the other 5 nodes. We don't need a path to ourselves. So in total, the number of paths are? How many? In the entire network. In the entire network, 30. Okay? For this node, there are 5 paths, and then we do it again for node 2. And then node 3, node 4, node 5, node 6. 6 nodes, 5 other nodes, 30 paths in total. And it's simply the number of pairs amongst 6 nodes. There's an equation for that. What is it? N times n minus 1 over 2. Where if you have n nodes, the number of pairs between those nodes is n by n minus 1 over 2. 6 times 5, in our case, it's not over 2 because we have paths in both directions. The divided by 2 is if we just consider one direction. Here we have, we have a path from node 1 to node 2. We have a different path from node 2 to node 1. Okay, so we need to count both of those paths. So the total number is n by n minus 1, where n is the number of nodes. Node 6 is the source, sending to node 1. So the source, we'll not do all of them. What's the path? Least cost path from node 6 to node 1. First, it's not always the same as the least cost path from node 1 to node 6. Remember, the cost in the opposite direction may be different. So consider or you need to calculate what is the least cost path from node 6 to node 1. Anyone tell me? I've calculated. I think you'll find it's 6, 5, 4, 2, 1, which is 4 plus 1 is 5, plus 2 is 7, plus 3 is 10 is a cost. 6, 5, 4, 2, 1. 6, 3, 1 has a cost of 8 plus 8, 16. So you can check the others. 6, 5, 4, 2, 1. I'm not going to write n, I'll just write 6, 5, 4, 2, 1, and it's a cost of, what do we say, 10, I think. Okay, we have that path. What's the least cost path from node 6 to node 2? Node 6 to node 2? Don't look at your picture, look at what I just drew on the board or wrote on the board. That tells us the answer immediately.
6, 5, 4.
It must be 6542. Why? All right, I can find the cost then. if this is the least cost path from 6 to 1 and it includes node 2, then a least cost path from 6 to 2 must be 6542. Why is that? Let's consider if it wasn't, just ignoring our picture. Let's say the least cost path from 6 to 1 was 65421, and a path from 6 to 2 was 632, for example. It's not in there, but if it was, then this could not be true, because remember the cost of the path is just the addition of the link costs. So let's say if this had a cost of 2, for example, and from 65421 had a cost of 10, and 2 to 1 had a cost, in fact it does have a cost of 3 in this case, then from 6 to 1 there will be a lower cost path than 10. It would be 2 plus 3. Okay. So if the lowest cost path from 6 to 1 is 542, then there cannot be a lower cost path from 6 to 2 than via 5 and 4. So this cannot be true. Because if it was true, then this wouldn't be the lowest cost path. Because if there was a path from 632 which had a cost of 2, then there should be a path 6321 which has a cost of, this is 2, and this is a cost of 3, which has a total cost of 5. Which means this would not be the least cost path from 6 to 1. So if we know a least cost path, in this case we know one to be 65421, then we automatically know that from 6 to 2 a least cost path is 6542, and from 6 to 4 is 654, and from 6 to 5 is 65. So we can use that information. You can use it to quickly calculate the least cost paths, and more importantly, it's used in how we store the paths in our switching nodes, in our devices. Anyone unclear on that point? It's an important point for the next step. Why it must be true that a path from 6 to 2 contains 5 and 4, a least cost path. Anyone awake? I know you spent many hours over the last few days studying, completing the assignment, but you've had one night's sleep. That's okay. Last night. Yeah. 65421, if we know that's the least cost path, then it must be, to get from 6 to 2, that must also be the least cost path via 5 and 4. Because if this was a least cost path from 632, then from 6 to 1, a lower cost path would be 6321. But we know that's not the case. So, given 65421, we know the following information. So this is not true. If we know from 6 to 1 is 542, then we know 6 to 2 is 6542. Node 3 we don't automatically know, but node 4 we do, 654. 654. Node 5. Node 3 you can calculate. It's, what is it? 653, I think. What about from node 5 as a source? Actually, we'll squeeze it in here. Node 5 is the source to node 1. If node 5 is the source, least cost path to node 1. Again, you don't need to calculate, the answer is here. From 6 to 1, 6, 5, 4, 2, 1. Therefore, from 5 to 1, it must be 5, 4, 2, 1. Because if there was a lower cost path from 5 to 1, that would be included in the least cost path from 6 to 1. So from 5 to 1, we immediately know it's 5, 4, 2, 1. And we could keep going, I'm not going to do them all. Source node of node 4 to 1. From here we know is 4, 2, 1. Sorry, let's get this correct. Path from node 4 to node 1 is 4, 2, 1. This segment of path. And from node 2 to 1, the path is 2 to 1. We use that knowledge to reduce what we need to store in each node. So what we do is we calculate these paths. Node 1 has 5 paths, node 2 has 5 paths, and then we store those paths in each node. Okay? Node 1, in theory, needs to store this information. So when it has a packet destined to node 3, it just looks up. Okay, to reach node 3, I need to send to node 4, and then it will send to 5 and 3. And if node 1 has a packet destined to node 5, it just looks here. Okay, the path to node 5, I send to node 4. And the path to node 6, I send to node 4. So we calculate the least cost path first, and then inside the node store that path information. But because of what we just discussed here, the fact that given this path, it must be true that a path from 5 to 1 is also 5, 4, 2, 1. And given 6, 5, 4, 2, 1, it must be true from 4 to 1, a least cost path is 4, 2, 1. Then what we need to do is only store the next node in the path. Node 1 calculates its 5 least cost paths to the 5 destinations and then stores in some table. To reach node 2, send to the next node 2. To reach node 3, send to 4. To reach node 4, send to 4. Similar, it's not so good a diagram, node 6 stores this information. Node 4, we've only drawn one of them. And how it works, if node 6 wants to send a packet to node 1, this tells us send to node 5, because that's the next node in the least cost path. Node 5 receives the packet, destination node 1. Node 5 looks into its table. To reach node 1, send to node 4, and sends it to node 4. Node 4 looks into the table. To reach node 1, send to node 2. Would send to node 2. Node 2 would then look in its routing table and say, to reach node 1, send it direct in this case. And then node 1 would receive it. So the result is that each node stores for the possible destinations the next node in the least cost path to reach that destination. And we get routing tables. Generally shown there for those 6 nodes in that network. For example, looking at node 6, to reach node 1, 2, 3, 4, 5, the next nodes were 5, 5, 5, 5, which is this table here. node 6 routing table, a directory called here, but I'll call it a routing table. To reach these 5 destinations, this is the next node in the least cost path to reach. For node 1, destinations, next node, 2, 4, 4, 4, 4. That's this information. And similar for the other nodes. This information is stored in each node if at least we use distributed routing. So node 1 stores this table, node 4 stores this table, and so on. And with that, the least cost routes are stored, distributed across all nodes. If we use those routing tables, then when we send a packet, we just look at who is the destination. If the current node is node 5 and the destination is 3, send to 3. If node 1 has a packet to send to 6, it will send to 4. Node 4 will receive it. Destination is 6, send to 5. Node 5 will receive. Destination 6, send to 6. It's reached the destination. And these are the common structure that is used in the internet today for storing routing information, called a routing table or a routing directory.